As we already mentioned before, complex roots usually come in pairs. So you will have the complex root and its conjugate under certain conditions. And we will now formalize this theorem. So this theorem is the conjugate zeros theorem. What does it say? So it says that if f of x, so my polynomial f of x, has real coefficients, so this is important, it has to have real coefficients, then complex roots always appear in conjugates. So this means that if we have a complex root, so if alpha plus I beta is a complex root and it has a certain multiplicity p, then also the conjugate is a root, so also alpha minus I beta is a complex root of the same polynomial, and it has the same multiplicity. So, and it also has multiplicity p. So for any polynomial with real coefficients, so it's very important that all the coefficients are real numbers. Then if you have one root which is a complex number, you also know a second root which is the conjugate of that complex number, and you know that both of them always have to have the same multiplicity. Let's then see what this means for the factorization of a polynomial. So I have a root, so a root alpha plus I beta. In that case, I also have a root alpha minus I beta. So for my factorization, this means that if I have a polynomial f of x, I can always write this due to the factorization theorem as x minus alpha plus I beta times x minus alpha minus I beta times some other polynomial f1 of x. Let's then rework this. So this is x minus alpha minus I beta times x minus alpha plus I beta times f1 of x. And then if you work this out, this is x minus alpha squared plus beta squared times f1 of x. Hence, this means that every polynomial can be resolved in factors that are either linear or quadratic, and they all have real coefficients. So if I make the complete factorization of my polynomial f, so if f has real coefficients and I make the complete factorization, I will always be able to write it in factors with all real coefficients of the first or the second degree, so linear or quadratic, but with real coefficients. Let's take a look at the proof of the conjugate zeros theorem. So we have f of x, which is a polynomial, so it is a n x to the power n plus a n minus 1 x to the power n minus 1 and so on up to my constant term a0. And I know that all of those, so a0, a1 up to an, they are all real numbers. Next, we also know that we have a complex root, so we have some complex root z, which is purely complex, so it's a complex number but not a real number. This one is a root. And the multiplicity of z is equal to p. These are the assumptions of the theorem. What we now have to prove is that on the one hand, the conjugate of z is also a root of f of x, and then we also have to prove that the multiplicity of z conjugate is equal to p. So we start with z conjugate. So is this also a root of f, yes or no? So what is this? So what happens if I plug in z conjugate? So we know that f of z, this is a n z to the power n plus a n minus 1 z to the power n minus 1 plus and so on. This is equal to 0. Why is this equal to 0? Because z is a root of the polynomial. So if we plug in z, by definition, it has to be 0. What then for the conjugate? So look at f of z conjugate. F of z conjugate is a n z conjugate to the power n plus a n minus 1 z conjugate to the power n minus 1 and so on. We then just apply calculation rules for complex numbers. We saw that the power of a conjugate is the same as the conjugate of the power. So this is also a n z to the power n conjugate plus a n minus 1 z to the power n minus 1 conjugate and so on up to a1 z conjugate plus my constant term a0. We also know that for a real number, a conjugate and the number is the same. So the conjugate of an is an itself. So this doesn't matter, it doesn't change anything. Why? Because it is a real number. So since ai is a real number, ai conjugate is the same as ai. Then we also know that a multiplication of conjugates is a conjugate of a multiplication. So this is also an z to the power n conjugate plus an minus 1 z to the power n minus 1 conjugate and so on. And we also know that the sum of conjugates is the conjugate of the sum. So this is an z to the power n, an minus 1 z to the power n minus 1 and so on to a0. And then the conjugate of this entire expression, which is just f of z conjugate. F of z is 0. And now we know 0 is just a real number. So the conjugate of 0 is 0 itself. So this means that z bar, so the conjugate of z, is indeed a root. Why? Because f of the conjugate is 0, so by definition this is a root of the polynomial. The second thing that we need to prove is that the multiplicity of the conjugate is also p. So we just proved that z and z conjugate are roots of f. And this means by the factor theorem that I can write f of x is x minus z times x minus z conjugate times some other polynomial f1 of x. If we write z is equal to alpha plus I beta, so z is complex number, so it's alpha plus I beta, then we saw that x minus z times x minus z conjugate, this is just x minus alpha squared plus beta squared times f1 of x. We know that f has only real coefficients. We know that this also only has real coefficients. There is no coefficient with an I in it. So f of x has real coefficients. The other term has real coefficients. So there is no other option than to say that f1 of x has also real coefficients. We cannot have any complex coefficient in f1 because by multiplying with x minus alpha squared plus beta squared, this would mean that f also has an imaginary or a complex coefficient, which is not the case. So f has only real coefficients, the extra term only has real coefficients, so f1 only has real coefficients. We knew that z was a root of f with multiplicity p. We have already used one of those roots, so it means that f1 still has a root z, so z is a root of f1. But now the multiplicity has gone down by 1. We have used one of the roots z, so the multiplicity of z is p minus 1. Then again we have f1 with real coefficients. We have z is a root, so this means that z conjugate is a root. We just proved this in the first part of the theorem. We just do it on f1 instead of f, so is a root of f1. And thus we can write, due to the factor theorem, that f1 of x is x minus z conjugate times another f2 of x, which is again a polynomial. And then we just reply the same reasoning. So we keep on doing the same thing. f2 is a polynomial with real coefficients. Z is a root of f2. The multiplicity now has become p minus 2, which means that also z bar is a root of f2, and so on until we reach the end. So if we continue it this way, we find that z bar is a root of f. We already knew this one. But that it has to have the same multiplicity. So the multiplicity of z bar is also p, which concludes proof. So the multiplicity is p, because for every z that we take out, we also take z bar out, so the conjugate of z. So we take out z p times, we also take out z bar p times. To conclude the chapter on complex numbers and the theory of equations, let's take a look at the arithmetic mean, geometric mean inequality. So the arithmetic mean, geometric mean, in short AM-GM inequality, will link the arithmetic mean on the one hand with the geometric mean on the other hand. So let us first define or explain what both means are. So suppose we have numbers a1 up to an. The arithmetic mean is then just the mean as you know it. So you sum all the numbers and you divide by the number of numbers. So in this case by n. The geometric mean is a variation to the arithmetic mean. So instead of making a sum of numbers, you make a multiplication of numbers. So you have a1 times a2 up to an. And instead of dividing by n, you take the power 1 divided by n. Why 1 divided by n? Because you have n numbers which you multiply, so it gives you a power of n. If every number would be the same thing, this would be a to the power n. And then you want to take the nth root out of this to go back to a. Same thing, the arithmetic mean. If all of them are the same number, this is just a itself. The inequality then tells me that a1 plus a2 plus an divided by n. So the arithmetic mean is always at least as large as the geometric mean. So the geometric mean can never be larger than the arithmetic mean, but there is one condition. a1 up to an, they have to be positive real numbers. So they have to be real numbers and they cannot be negative. And then there is only equality. So equality only holds if all the numbers are the same. So if a1 is a2 is equal to an. In that case, the arithmetic mean and the geometric mean are the same and they are equal to this number. Let's take a look at some of the applications. So assume that we have a sum of three numbers. So the sum of three numbers is equal to 7. What is then the maximal value of the product? Let's say that the three numbers are a, b, and c, so we know that a plus b plus c is equal to 7. And we also know the arithmetic geometric inequality, so we know that a plus b plus c divided by 3 is always larger or equal than a times b times c to the power 1 over 3. We then know that a plus b plus c is 7, so this is 7 divided by 3. And so a, b, c, the product, can never be larger than 7 over 3 to the power 3. So the maximal value of the product, if the sum is equal to 7, is 7 divided by 3 to the power 3. Then for the second example, take a rectangle. So you have given a rectangle for which you know that the perimeter is P. What is then the maximal area of that rectangle in terms of P? So again, we have to link a product with a sum. So AM-GM inequality always links a product with a sum. If we look at the rectangle, we can say that one of the sides is A, the other side is B. We know then that the perimeter is 2A plus 2B, so it's A plus B times 2. And we know that the area is A times B. So we have on the one hand the perimeter P 2 times A plus B, and on the other hand the area AB. We know that the perimeter is equal to some fixed number P, and then we apply the arithmetic geometric mean function or the inequality. We then know that A times B, the root out of A times B, is smaller or equal than A plus B divided by 2, which is equal to P divided by 4. So the maximal area, this is then P divided by 4 squared, so it's P squared divided by 16. If you then think a little bit further and you say, when would there be equality? When do we get the maximal area? We get the maximal area if A is equal to B, so if we get a square.